All right, let's go ahead and get started, everyone. All right. So I've graded all the exams. I'm going to pass them back next class, so on Thursday. I'm going to offer some little extra credit things that you can maybe improve your scores with. So we're going to move on away from rotation, angular momentum, and torque, and all that. We're going to completely change subjects, kind of. We're always talking about physics whenever we talk about pretty much anything. So right now I'm going to veer into fluids and solids. I'd say this is one of the, I could say lighter chapters. I might actually finish the whole chapter today. So in order to, make it more enjoyable, I brought out just so many demos that I'm going to just be doing today. So let's go ahead and get started. To start out, we need to look at the states of matter. So all objects, all physical things have mass, but how is that mass arranged? These are called states of matter, and they're going to be one of 4 things that we'll see in daily life. There is a 5th one we don't see in daily life. We probably already know that the first three, there's solids. These are objects that, the elements, this table, are made of, specific atomic structures. These are highly ordered structures of atoms or molecules. As they group together, they sort of settle down and find a neighbor and become one continuous thing. Next one is a liquid. Now imagine if you take a solid, and I think the perfect example is ice is a solid, and imagine it turning into water. So it goes from this thing that has structure, it has a shape. And then you add some heat, you add some energy, that sort of fixed structure isn't fixed anymore. It sort of disintegrates, and that's what I call right here. It's a closely packed free molecule. So these molecules of water, they still keep their same shapes, but now they're free to move past one another. We have a gas, so keeping with this water theme, take that ice cube, melt it into a puddle of water. You continue to heat it up. You continue to add energy. All of those, barely moving molecules, they'll move past one another. Pretty soon you're adding energy. They're going to be moving past each other very quickly. And so they turn into another phase of matter, another state of matter, a gas. So these are highly energetic molecules that will move their own, on their own path. We take water, ice goes into water. What are we doing? We're adding heat. Water into a gas, we're adding heat. We're adding more energy. So if we take that gas, say we take, the steam that comes off of heating up this water, if I keep heating it up and heating it up, that atomic structure of water, I don't have a water molecule present, heating it up will actually tear the atom or the molecule apart. So let me do a little show and tell. We have this kind of represents a solid, highly structured. And on the atomic level, things are kind of jiggling all the time, kind of like this. Then as we heat up, these little links, they all kind of break. You know, one might break, another one might break, and then this whole separate chunk will be floated around somewhere, moving past one another. And maybe you heat it up more and more, the links between molecules will separate more and more. So imagine this is water. I don't have a specific water shape molecule right here. But then heat it up even more, all of these will break. And maybe there's just a couple things holding this molecule together. A plasma, at the very end, is highly energized charged particles. So that's when the atom itself starts to separate. You're adding a lot of heat. So this is going on in stars, in our sun. Our sun is made of mostly helium, just the element of helium that is highly energetic. This is a plasma. So I have, let me put the other slide up first. So I have, like that. I have this little demo here, kind of represents what this phase change is doing. I'm adding heat, going from a solid to liquid, adding more heat, changing into a different state of matter. So you can consider this, let me actually get it going first. I said a solid is kind of jiggling still, right? So consider this a solid. It's highly organized and nicely sort of oriented. This is like a loose demo of this, because these are like spinning. But then I'm going to add more energy to this. So it goes from this solid, they're nicely packed together. I'm going to add more energy. So now we're in a liquid. It changes into a different form. I add more energy. All of the atoms are starting to get very energetic as they push on the surface of this little barrier. As you start to cool something down, you take the water, you put it in the fridge. You take water, put it in the fridge. It starts to take away some energy from the system. Turns back into a solid. So going from each of these phases is just adding energy. All right, that's loud. Okay. Another cool thing about this, about solids, I should say, is that you can have various differences in just how the solid is oriented. So if you go into chemistry or geology, you might start looking at stuff like this. So here we have, this is our, right here we have, this is graphite. And right here we have the atomic structure of a diamond. So what is common between graphite, you know, the stuff in your pencil? What's common between those two? Graphite and a diamond.
made out of carbon?
They're both made out of carbon. These are the exact same elements in this one and this one. So just on the arrangement of how the solid is oriented, you get graphite, and that's what these little purple connections in the middle. The reason we use graphite is because these purple connections break real easy, and so we can write on the paper. It leaves some carbon behind on the paper. This is a very, very, very strong structure. It's hard to bend or break. It's hard to get carbon into this form. That's why it takes a lot of pressure to actually get each and every one of these carbon atoms oriented like this. So these are the same elements, just arranged differently into different solids. Okay. Leave that over there.
Okay. Professor, I was going to ask, so when a gas goes to plasma, are the atoms like breaking apart?
Yeah.
Like
Sometimes the atoms themselves break apart.
So, is plasma involved in like nuclear?
They are exactly. That's what's going on in the sun. There's constant nuclear reaction. So the atoms splitting give off even more energy, and that's why the sun is just a source of light, because that's pure energy. Yeah, so I draw like a water molecule. We have oxygen and 2 hydrogens. So we have a bunch of these floating around, a bunch of Mickey Mouse heads. The molecule itself may be intact, and that's a gas. You could say that's a gas of, maybe it's a more complex mixture. Maybe we have this gas of just pure steam. It's called steam water. But then as soon as these start breaking up, maybe I add more energy, and now that's just an oxygen, and the hydrogens go somewhere else. Those are the charged particles I'm talking about. These are no longer together. It's just a big ball of mass called plasma. Then if this hydrogen, then it starts to separate. That's going to be the nuclear reactions in stars, stuff like that. All right. So we have these states of matter. So let's go on to describing how the things are arranged. So why do things fall into the arrangement that they're in? So why do some solids take up so much space when others don't? So example, the diamond and the graphite. Why do they create this shape? Or maybe how can I begin to think about this? What is even the first step to understanding that? I need to look at the density of the object. So comparing 1 kilogram of paper, I have 1 kilogram of paper here, about that much, versus 1 kilogram of steel. That's only this much. Why are they different sizes? I also have 1 kilogram small steel ball and 1 kilogram large steel ball. So why are these different sizes? Maybe something's going on here. But they are the same mass. How can I describe this? Let's go to density. So it's however the atomic structure, like the diamond and graphite, It's all based on the structure of the material. So density, whenever we say density, we are talking about how many atoms of that element or that material there are in a specific volume. So I'll say just very general. It's the mass of all of the atoms over how much volume. So that's it kind of in words. The density formula is this. It's rho. It's a fancy looking P, sort of slanted. Greek letter rho equals mass over volume. So if I'm going to compare the density of two objects, I just say, okay, so what is the total mass of this diamond? How much space does it take up? I can find the density of this. What is the total mass of this graphite? How much space does it take? And that is the density. So that's the secret of figuring out how to tell the difference between these two. So if I say I have 1 kilogram steel ball, which one am I talking about? I'd also then include the density of the steel ball. You can know which one I'm talking about. That and that. Yeah. So we're able to describe how objects, are formed. Maybe we'll be given an element. We can also use its density. Figure out what I want. Okay. Could also use its density. What if we have a liquid? Can we do the same thing with density for a liquid? Well, yeah, we can find a set amount for density, how much mass of the water in this much. More typical thing you'll see with a liquid is finding the pressure. How much pressure does a liquid exert on, a system or the walls of a container? So what is pressure in a fluid? So pressure is force per area. So this is, I'll just say force. So I have a demo for this in a minute. Let's say we have this container of water, and we look at the pressure that the water exerts on the sides of the wall. So I've already shown you how water can be sort of this free moving thing. It's going in every direction. So if we zoom in on the side here, so I'm going to take a little slice, I'm going to zoom in. All of those individual little molecules, let me make the wall. There's the wall of the container. So all of those individual little molecules of the liquid are going to be, randomly hitting the sides of the the wall of the container. So maybe that one comes in, bounces off that way. Maybe this one goes like that, bounces off that way. You know, they're going every which direction. So add one more. And every single one of these little collisions, they're just very tiny little collisions, against the wall of the container adds a little bit of force inward. So I'm going to make that this red. Small force, make it a little brighter. There's a small little force from that molecule. There's a small little force from that molecule. Each one of these individual small little collisions is just sort of averaged together to make this pressure calculation. So I'm going to see how much force this liquid's applying on the walls in a specific area. So I'm going to say like a slice that big will have a certain pressure. You know, I'll have a specific area that it's colliding with. We can use pressure, we can use this calculation of pressure to actually be, you know, very useful in, you know, hydraulics, knowing how to properly make and maintain like big tanks of water, big aquariums. We need to know pressure for those systems. So let's look at, you know, an example of that. This is a hydraulic lift in like a, you know, regular auto shop. The little diagram on the left is very dramatic. I have a kind of real one right here. Like that. What's happening is that inside of this lift there is, it will use like hydraulic fluid, and it will say this is an incompressible fluid. So I'll put it in quotes, incompressible. Every fluid is a little bit compressible, but for the grand scheme of things, we can always say for this class they're incompressible. What I mean is like no fluid is squishy. You can't like squeeze it. So we have on the left side over here, we have a force being applied downward. That's force 1 being applied downward, and it's being applied to a specific area. You imagine these as tubes of different diameter. So if I apply a force on the left side, force over here, and the liquid inside of this container is not going to be, you know, squeezed or compressed, it has nowhere else to go but lift the car up on the other side. So let's do this. We'll say the pressure on the left side, the pressure for 1, is equal to force of 1 over however much, you know, however the diameter of that side is. You know, since it's going to be a circle, like this. And on the right side, we have that. And by me saying this is incompressible, I'm saying that the pressure everywhere inside of this little device, this little system, is the same. So I am saying P1 equals P2. And that gives me the ability to relate these two equations to one another. I can say that since P1 equals P2, I could set the equations equal to each other. And let's just finish this out. Let's say F1 equals A2. There we go. Now, as soon as I see this problem with values, it might become more clear that there's going to be a smaller force applied on the left side over here. So, applying a force downward, you guys gotta just believe me, I can't put a mass on this. Pushing this down on this side is a lot easier to do, and it is lifting this side with a greater amount of force. As soon as we do that A1 over A2 ratio, we will get some sort of lift. That's how we're able to lift things with this type of hydraulic press. All right. Very simple. I think this is like one of the only hydraulic problems that they ever make you do. So we're going to do it right now. So we have same type of system. These are circular tubes. On the left, it has a radius, or I should say the large one has a radius. So this over here is R2 of 20 centimeters. The small piston has a radius of 2 centimeters. And what we want to know is just how much force do we need to apply to lift, or at least hold, I should have said at least hold, a car with a mass of 1,500 kilograms. So I just put like a car over here. Okay, 1,500. And we can assume this is an incompressible fluid, so we can say that the pressure is equal everywhere inside of this system. So F1 over A1, F2 over A2. So what we want to know is how much force do we apply on the small tube? How much force over here? So I'll put the arrow right here. And we're going to raise this car. Okay, so we have F1. Oops, sorry. So F1 over A1, 2 over A2. It's pretty much the same result as last time, but this is something we have to fill out now. So what is the force F2? So that's going to be the force on the right side, and I should have said at least hold, but it says to raise. So we have the mass of the car, and so that's m2 times gravity. And these are radiuses. That's the problem describes them as radiuses. So what's the area of a circle? So that's pi r squared. Nice, specifically r1. This one down here is pi r2 squared. All right, so 1500, 9.8. I should be writing these two. That's kilograms. R1 is, I need to change to meters before I do anything crazy. Okay, so we have 0.002, nope, 0.02. Okay, I didn't do this beforehand. Actually, I might have. Let me check. Okay, we can see that the pi will cancel. That'll make it easier. We are going to do this. We have about 147 newtons. Let me do this real quick. So in comparison, at least so we can see what's going on, we're applying 147 newtons on the left side, and we're lifting up a whole car that I already did the math. This right here is 14,700 newtons. So that small amount of force is producing, something that can be a lot of force on the right side. Okay. So, learning about pressure, learning about things that, just an average that is applied to a surface, something like that. What if we have a really large container, a really large object? I can say pressure is force per area, but what if we have, what about pressure? Yeah. So what about pressure at, various depths? What about if I have a large container of water or something put into water that is very large? If we have this, and imagine this is like a, SeaWorld aquarium. This thing is, like 30 feet high. We have a difference in pressure from the top right here. There's a small amount force on the wall. We go down farther and farther. If you guys have ever gone swimming, the swimming pool, if you go to the deep end, you go all the way down to the bottom, you can feel a difference in pressure. You can feel it on your body. What's actually happening there? And we say it's pressure, and then we forget about it once we come back up to the ground. What's happening is all of the water that's on top of you is pushing down on you. So as you get farther and farther down, there is a bigger and bigger pressure. So we have larger forces on, things that are significant of size. So I'd say wouldn't be for a problem if I had a really small tank, something like this. But as soon as things scale up, we need to consider these differences. So we have original pressure, F over A, and I can't just take the whole area of that side because the the force is different places. So I say is the pressure is equal to the initial pressure plus the density of the water times GH. And so that's just wherever I am located in this, huge aquarium or submarine down miles below the surface. I can say, something right here is so far under the surface, H, I can find how much more pressure is being applied to this thing. Okay. All right. Here we go to buoyancy. Now, buoyancy, a little bit, I'd say this is all kind of the same thing. We have pressure once we're under the water. We're swimming in a pool. We feel this heavy weight of water above us. And if you've also been swimming, you know that there's like this natural upward floating that goes on. Why do some things float? Why do we float in water? I have a friend who doesn't float. Why do they sink? So if I have this, so the reason is, in general, you can say density, sure, but there's something else happening. I hope this holds water. Okay. Okay. So these two spheres I was telling you earlier, they both weigh the same. One of them sinks. That one floats. Why? You look at a river, why does wood float down a stream? Why do the rocks sink? Again, you could always say density, but there's something more. Where did my pen go? There it is. The secret is Archimedes' principle. And it's also like my picture. Why do those huge cargo ships made of metal actually work? We need to know what Archimedes' principle is. So it's a big long statement. I wanted to put exactly what your book says. I'll describe it in a minute. Hold on. Okay. So for things to float, for me to put this ball in the water, initially there's a certain level, there's a certain height of water in this container. This object is sort of entering the scene and it has to push some water out of the way. So that's a part of it. So that is what Archimedes' principle is primarily saying. It's saying however much water, however much fluid an object tries to push away, the weight of that fluid is equal to this sort of upward buoyant force. He describes it as this object is buoyed up. So we have like us floating in the water, we are a cube, and we get this upward force that is called the buoyant force. So, in more technical terms, we always need to know that we have the buoyant force is equal to the weight of the displaced fluid. So that'll be the density displaced fluid times volume of the displaced fluid times gravity. Buoyant force. So we take that idea that things that are put into a fluid have to push the fluid out of the way. So how much fluid, how much water is this little sphere going to push out of the way? It's only going to be a little bit. It's only going to be however much size this object is. There's a very small amount. So it's only going to push a little bit of fluid out of the way. So the volume is small. There's a very small buoyant force. We have this large sphere. This large sphere can push a lot of water out of the way. It's got this very big base. So it can push out a lot of water on the sides. So that means all of the weight of that water is going to help push it upwards. We have more volume, so we have a bigger buoyant force. If you want a better picture, I guess, I had this. So same thing. This was if I couldn't find the spheres. So take an object, put it in the water, and it displaces a certain amount. So that is volume of displaced water. And since this object sinks, it's displacing its own volume of water. That's why I have that sort of separate cube over to the side. It's displacing that much. It pushes that much up. Okay. So we have. No, I'm not going to make you guys redraw this. So we have that. I might start at that point next time. But we're going to have a little story about Archimedes and his Archimedes principle. So he was sort of this mathematician in, I believe, Italy, and new king in town said that he was a little curious if one of his goldsmiths, his jeweler, the king was thinking that the jeweler was ripping him off. Said, "Here, take my crown. I don't think it's made of pure gold. I want it to be pure gold." And he hands this big solid chunk of metal to Archimedes. And he's tasked Archimedes, he said, "Go ahead and see if this is pure gold. Make sure you don't ruin my crown. And get back to me with an answer." And if the king tells you to do something at that time, you pretty much do that until you can't. So what he devised, he didn't start out with this experiment. He didn't have the right answer. He couldn't figure it out. The story, or the saying goes, is he was taking a bath and he filled the water level up too high. He filled it up to the very edge of where the bath sits. And as he went to go sit in the bath, all of the water spilled out, or a good amount spilled out. He said, maybe I can use that. Maybe that's a principle or an idea I can use. And the saying is, he yelled "Eureka" and ran down the street. I don't know if that's true. Right. So we have this principle. We're seeing how much fluid is displaced. Whether it's a small object, it'll displace only a small amount. If it's a large object, it'll displace a lot of fluid. This is why, logs, big sort of timber things will float. This is why, I don't have pens up here. This is why ships, big cargo ships, even though they're made of metal, they will float. And that's because cargo ships are shaped like this. Like that. There's a lot of stuff up here. And the ship itself a lot of it is made of air. It pushes away a lot of water. And so that's a big volume that is helping give this buoyant force upwards. Same thing with a hot air balloon. So even though gas is a different state of matter, you could still consider it a fluid. So the density of air inside and outside of the hot air balloon is different. We have this pushing away of the fluid. So that's why a hot air balloon will rise. Okay, I think that is that. I have a small demo of pressure I want to do, and then we'll be done. So we'll leave it right here. This right here. And if you guys want a challenge after today's class, you can come down and take a look at these. So we have, I'm not going to give you the answer right now. You can come down and take a look. We have this thing in this bottle right here. We have this, it's called a diver. And as I squeeze the bottle, it goes down. As I let go, so what's going on there? Also, I have this. These are two colored beads. They make this nice, weird line right in the middle. Then they separate. Then they move back together. So that's a little puzzle for you guys. For my pressure demo, let me open this up. Too much stuff. So we have pressure. Let me put pressure on the board. Equation pressure. Force over area. So if I apply a force to a specific area, we'll get pressure. And we'll do this. So I have this nail sticking up. It's a single nail. And I'm going to apply a pressure to the balloon. So a force, not pressure. I'm going to apply a force to the balloon. I'm going to put one of these 0.5 kilogram masses on top. And we have this very small area for the nail. What's going to happen? What's going to happen to the balloon? Going to pop? All right, let's see. All right. You guys are right. All right, now I have sort of a set of many nails. How many? There's about 10 by 10. Probably, yeah. 10 by 10. So there's more nails. I'm going to do the same thing. Is it going to pop this time? No. Why? There's a larger area, right? So I can put this on here. Okay? It will just keep going. Just put it on. That is 2 kilograms. 2.5. So having a bigger area, bigger denominator, reduces the amount of pressure on the object. So this balloon is safe. This balloon is perfectly fine. I put a lot of, you go pick that up, that's heavy. I was pushing down really hard. So if someone wants to come help me lift something out of the back, that'd be great. Someone help me lift. Yeah. If you want, yeah. All right. Right here. Perfect. Right here I have a bed of nails. Show pressure.
It's fear practice.
So, this is a bed of nails. I've already proven to you having more area reduces the amount of force on the thing. So, right down there. Same thing, just nails, right? So, you have this, and it's perfectly safe. All right? Do I have any volunteers? All right, yeah.
Why did you put a pillow there if it was completely safe?
Completely safe? Well, look, I didn't say it was comfortable. All right, so that's the end of class. If you have, or if you want to volunteer, come down. We'll do that first. Oh, yeah, I'll take any volunteers. Yeah. Come on down. Just go ahead and then go ahead and sit down. Hands on the outside. Yeah, you're going to sit down first and then you lay back. Try not to speak while you're on there. Good. It doesn't hurt that much.
Will it really amplify your
I say if you scoot, so they are still nails, they are still pointy. So if you do, I could like help you up, more encouragement. When are you going to ever try this again?
Well,
When are you ever going to
on Saturday.
be able to try it? You see? So I'll tell you guys more about that next one.
Oh, it's next time.